All right, thank you. So my original title was Subfactors and Planar Algebras, and I changed it to Planar Algebras and Subfactors because I'm not going to talk about subfactors at all today, actually. So there's lots to say about planar algebras and diagrammatic categories, and it sort of seems like one of the themes of today has been that we're drawing pictures for stuff. So instead, I'm going to go into that in more detail, and I promise if you're sitting in the audience waiting for subfactors, there will be subfactors on Thursday. Okay, so let's do some math. Okay, but that's not actually what I meant to say. Let's draw some pictures. Okay, so an excellent lesson I learned from my advisor is that you have to have taste, and it doesn't really matter where your taste comes from, but you have to have some things that you think are more interesting than other things, or else, especially in a semester like this, you'll just be pulled in a million different directions. And for me, it so happens that that thing is drawing pictures to do algebra. Okay, so I think that's amazing. It's certainly not the only amazing thing that's happening this week or this semester, but that is my favorite part of the whole field. Okay, and so what I'm going to do is I'm going to move from the specific to the general. So I'm going to start by talking about something called the temporally-Lieb algebra. And I'm going to move on to defining a more general thing called planar algebras, which themselves are a sort of specific formulation of diagrammatic categories. Okay, so references. Right, I'm going to put this at the beginning of the talk because I'll forget about it if I leave it for later. Okay, I'm going to suggest Vaughan Jones's foundational paper, Planar Algebras. I think it's called Planar Algebras 1, but I do not believe there is a Planar Algebras 2. This is a great place to go for examples. So he has a dozen examples worked out in some detail, and if, like me, that's the way you prefer to understand things, this is a great place to start. On this matter of taste, when I was a grad student, I spent a long time trying to figure this stuff out, and when I sat down and wrote my thesis, I tried to write that down. And so I am going to recommend my thesis if you want my particular treatment of how I think it's the sort of shortest route to understand planar algebra. So nowhere near as thorough as Jones's. But then for diagrammatic categories, I want to recommend a very new book, which nevertheless the library here has. Chris Heunen and Jamie Vickery have a book called Quantum Categories something something or something. Sorry. Categories for Quantum Theory. Okay, and this has a very careful treatment of diagrammatic categories in it. Okay, so let's get started. A temporally Lieb diagram is a non-crossing pairing of endpoints drawn on a line above and endpoints drawn on a line below. So for instance, just any way you can connect these points up among themselves as long as the lines you draw don't cross. So here's an example of a TL7 diagram. Okay, and when I say just temporally lieb or temporally lieb n, I mean make a vector space that has these diagrams as its basis. Okay, so in other words, we have formal addition. Okay, but in fact, this is more than a vector space. This is an algebra. We have a multiplication on this. So multiplication is by stacking. Okay, let's see. If I have this frowny face and I multiply it by this diagram, then I'm just going to put them one on top of the other, like so. Okay, and I should have said that these TLN diagrams are only considered up to planar isotopy. Okay, so really they're combinatorial things. And when we stack them together, we say, well, could make this look a little bit smoother. So this is really just the same thing as the diagram that looks like this. Okay, so far so good. But what if we tried to multiply them in the other order? So then we would have this on the bottom, and above it we have this. And what's gone wrong? We have some extraneous data. We have this little loop in the middle that is not accounted for in the data of a pairing of points. Okay? And so what we do is we throw it away, but we remember it was there by multiplying the resulting diagram by delta, which can be a variable for now. Okay? We haven't remembered what region that loop appeared, and we've just remembered that it was there. If it appeared anywhere else, we would have picked up that same factor. Okay? So just a little bit of more information than just throwing it away altogether. What's the identity for this multiplication? Everyone show me use your hands. Show me the identity. Okay, excellent. The identity is this diagram, right? Take a diagram, stick it above this or below this, and you have this, get back the same diagram. Okay. Now, so we have temporally lieb as an algebra now, right? We have a vector space, we have multiplication. Oh, I should say, this is how you do it for individual diagrams. You should, of course, take the linear extension of this to sums. Okay, but there's more structure, too. There's a trace on temporally lieb, and this is the trace we get by taking our diagram and taking all those strings on the top and all those strings on the bottom and tying them together. So this goes here, this goes here, this goes here, and this goes here. And now we maybe have to scratch our heads for a second to see how many circles is that. Here, if I shade it in, then it gets a little hard. Then at least you can tell the inside and the outside apart. And then you can see that I can retract along this. And what I end up with has one loop inside the other one. And so the trace of this original diagram, like that, is delta squared. Okay. Now, like Eric said, more adjectives means we can do more, that we have sort of more concrete things. So we also have a star structure on these. Okay, and this one's pretty straightforward, right? The adjoint of a temporally Lieb diagram is the diagram you get by flipping it over. So it looks like this. I'm going to be doing a lot of proof by example in this talk because saying this stuff rigorously takes a lot of time, and often the examples are clearer anyhow. Okay, so we have a star structure, and this, together with the trace, enables us to make a bilinear form. Okay, and very soon I'll need to know a little bit more about delta, so let's start keeping track of that. So the bilinear form on TLN delta, if we apply it to x and y, this reflects y and multiplies it with x and takes the trace of that. Okay, and so really this is, here's y star, here's x, and then we trace them off. This is more symmetric than it looks because we could just pull y around to the bottom. Okay, so we have this bilinear form, and under certain circumstances, which I'll come back to on Thursday in my second talk, this bilinear form is actually positive definite, and so it's an inner product. Okay, so that's, if delta is a real number greater than or equal to 2, then this is an inner product. And
do you consider algebras over real numbers or complex?
Probably complex.
Well, then you probably want to consider Hermitian, right?
Yes. Good point. Thank you. Okay, so having an inner product is great. It means we have all the tools of geometry available. And I don't mean, the complicated tools of modern geometry. I mean things you expect to be able to do with norms and using inner products to measure angles and things like that. Okay, so this is a great situation to be in, but I don't actually need to say more about it today. Okay, and one last point about the structure of temporally Lieb is that the TLNs aren't sort of separate independent characters that never interact, right? They kind of all form a family. So TLN embeds in TL n plus 1 by taking any TLN diagram and adding another string to the right. Okay, and so this really gives us a whole family. All right, and I guess there's something sort of implicit here, which I'm not going to talk about more, but as an exercise, you could convince yourself that this plays nicely with the structure we've already created. Okay, so exercise, check that this inclusion respects multiplication, trace, identity. I guess for trace, there's a little bit of subtlety that comes up. And something, something, trace. Okay. Now, what I'm going to tell you about today is planar algebras, which temporally Lieb is the first and most important example of. Okay, so a planar algebra is a family of vector spaces one for each natural number. Okay, so they're vector spaces. But they're vector spaces for which we can interpret these drawings as having meaning. Okay, so I'm going to phrase that as we have an action by the planar operad. Okay, well, don't be scared of that word operad. I use it all the time, and literally the only thing I know about it is that the planar operad's an example of it. Okay, we'll see in a second that this is not some weird abstract thing. This is just spaghetti and meatball diagrams and the things you can get by combining them. Okay, now. So we start with our plate, okay? And we have some meatballs on it. If you're sitting in the back of the room, can you tell the difference between the purple chalk and the white chalk? No. Okay, let's try something else then. Okay. So we have a plate, we have meatballs, and then we have some spaghetti that connects them to each other. Okay, but this is special spaghetti that's not allowed to cross over itself. Okay, and all of its stopping and ending points have to be on one of the inside circles or one of the outside circles. Okay, so we have a outside boundary. We have multiple inside boundaries. We have non-crossing strings connecting them. I guess I said this right. I said that every endpoint of one of these strings has to be on a meatball or the plate. But that doesn't exclude the existence of spaghettios, right? A spaghettio has no boundary, and so that's fine. Okay, so that's included in the non-crossing strings. And then the other thing we need is an additional piece of information, which is a marked point on each of the boundaries. Okay, and the reason for this we'll see in a second, but for now, just plonk one of these markers down somewhere. Right. So marking the intervals divided up by the strings, not the strings themselves. Because we want to be able to compose these together. Okay, so I'll try to start with not too complicated an example. Okay. If we have this, and we compose it with this, then, wait, not done yet. Okay. So we can compose two diagrams if the outside number of points here is the same as the inside number of points here, in which case we pick this up and we shrink it down, and we maybe rotate it until the stars match up, and then we plunk it down inside, and then we no longer have an outer boundary here and an inner boundary there. We just have a single planar diagram again. And when we do this, let's see, this gets rotated. I'll draw that in for now to make this part easier. And then here we have this. And those stars are now here. And so the result is this planar diagram. Okay. So far, so good? Okay, cool. So what does this have to do with this family of vector spaces we had up there? Well, we are supposed to have an action. Oh, yeah, so planar diagrams with this limited composition form an operad. In my point of view, that's what an operad is. It's a gadget where you have a bunch of things and you can compose some of them. Okay.
Don't you have composition when you fix one of the holes in one of them and stick the other one in that hole?
Yeah, that's right. Yeah, and you're absolutely right, actually. We do need to be a little bit careful about specifying which hole we're sticking it in. You know, here I gave an example where there was only one choice. Yeah.
So if the number of strands don't match, do you get 0?
Yes, or undefined. Yeah. Okay, now the idea of saying that these V's are a planar algebra is saying that these are also allowed inputs into one of these planar diagrams. Okay, so a planar diagram is supposed to give us a multilinear map from, okay, so you count up the strings around each of your input disks, and that's which vector space you take your input from. So tensor product of the inputs to the vector space corresponding to the number of strands around the outside boundary. So up here, what does this give me? This gives me a map from, let's see if I can count. So the one down at the bottom is V3. And that next one is what? 1, 2, 3, 4. And then we have 6 up there. And my outside boundary has 7 strings around it. So our input from V3, tensor V4, tensor V6, those inputs give us something in the space V7. And this is what a planar algebra is. Okay. And what makes this hard is that whatever rule we have for taking some inputs and a planar diagram and coming up with an output, it needs to be compatible with the operad structure here, with the composition. Okay, so compatible with composition so let's look at this diagram here. This took 2 inputs in V3 and gave an output in V8. So, okay, but remember this came from 2 other planar diagrams, and so we should be able to accomplish this same map in 2 steps. First, sending V3 tensor V3 into V4, according to this diagram, and then here, taking something in V4 and putting it in V8. Okay, and so to say that it's compatible with composition means this diagram and every diagram like it commutes. Okay, and so that is where the work is if you want to prove that something is a planar algebra. Okay, so our first example is temporally Lieb, which lets us avoid that difficulty. Yes? It does. I should be more careful about that. Yes. Okay. And the action by planar diagrams is just to insert your temporally Lieb diagram into one of them, basically so you've plugged up all the holes, and then smooth out your strings and throw out any loops you generated, and you get back another temporally Lieb diagram. So this is not actually all that interesting an example, or rather, it's an incredibly interesting example. It doesn't really illustrate the subtleties here very well. Okay, and so the next thing I want to do is a more complicated example, which is the example of a graph planar algebra. Okay, and this is made up of the path algebra on a graph. And so you may have seen this in other algebraic contexts before. So just for the ease of notation, let's let gamma be a simply laced graph. And then my space Vn is going to be loops on gamma of length n. Okay, now, if you've seen this example before, how do you multiply two loops together? So we're going to approach this planar algebra question a little bit backwards. Well, we're going to do what we did for temporally Lieb. We're going to give meaning to a bunch of individual diagrams and then see how they all fit together into a single framework. Yeah. And say the span over the complex numbers of those loops. All right, how do we multiply paths together in algebraic topology or in path algebras or anything? Excellent, yes. So we want to concatenate them. Now these are loops, and so they all have the same start and end point, right? So the answer is we concatenate. If we have a loop L1, we just do L1, and then we do L2. Is this the only multiplication you know of on paths, on loops like this? Somebody might have encountered a different multiplication here. Okay, so there's another one. This is A1, A2, where let's imagine our loop has even length. Okay, so on an even loop, say, our loop consists of two paths, right? A path from start to finish, and then a path in the other direction from finish to start. Maybe we'll call that P2 star. So we have P1, P2, and something else, P3, P4 star, that say starts at the same place and ends at the same place. And we can multiply these together by contracting before we concatenate. In other words, if these are the same path, if P2 is the same as P3, then we just take the path given by P1, P4. Okay, now, the diagrams that represent these multiplications we've been doing look like this. So for concatenation, I start with something with n endpoints, with n, a path of length n, and I have another path of length n, and I get back a path of length 2n. And so this diagram at least passes the minimal requirement of giving the right type of thing back. Okay, and for this example here, what I'm going to do is, and this looks like the operation in Temperley-Lieb. I connect half the points to the other half of the points. And then the other ones go to the outside. Okay, so maybe an example will help illustrate this. Let's take our graph to look like this, and we'll name our vertices A, B, C, D, and E. And what if we took the path that went from C to D to C to E to C to B, and then to A and to B? So start here, go out here, and then all the way out here. Okay, and then we end up back at C. Okay, and now let's take the path that starts at C and goes to A, and then goes and visits E a couple times. Okay. What you should imagine is that what this path does in this diagram is comes in and just labels each of the regions around this circle. So C, D, C, E, C, B, A, B. So that one is down here, and this one will go in here. And so we get what? C, B, A, B, C, E, C, E. Now, what do you notice about this? The regions are labeled consistently. The regions that have more than one potential label actually always get the same label. And so the result of taking the first half of this and combining it with the second half of this is just what you get from reading around the outside. So you get back C, D, C, E, C, E, C, E, and then back to C. Okay, and so this is why this diagram acts in this way to multiply these together. Now, what about concatenation? So concatenation should, well, let's say we wanted to let this act on a couple paths. These will start at C2. How about CD, CB, and then CBA, BC? So we go C, D, C, B, C, and then here we go C, B, A, B. And when we read off the result around the outside, it looks like C, D, C, B, C, B, A, B, C. Okay, and so this is the path we get by first traversing this path and then traversing this path. So, if that's all we have to do, what should the trace do? Okay, so the trace diagram, remember this one also works on loops of even length. It's going to look like this. So what effect is this going to have on paths? Or sorry, on loops. You have to come back the way that you went out. Absolutely, right? So this is saying that if I go from C to B to A and then back to B, then as I traverse back, if we're going to have a consistent label here, this needs to be A and B. Okay. And probably you can see the general picture here. But there's sort of one thing that I haven't specified. Okay? So maybe there are two things, but one of them is probably clear. Right? One of them is, what if you plug in things and you get two conflicting labels on the same region? You get 0 back. Okay? Those things don't multiply. What if not every region gets a label in this process? Okay, so we have the inclusion map that we had in temporally leap. And say we go C, B, C, B. And then we try to read around the outside. And we haven't specified what vertex is in here. So in this case, we just sum over all the possibilities. Okay, so the output of this is C, B, C, B, C, B. So that's like the new bit we stuck in, but it could also have been C, B, C, D, C, or C, B, C, E, C. Okay, so all three of those, there's no way to tell which of those three possibilities we prefer, so we just take them all. Okay. Cool. So I promised I was going to go from, oh yeah, so okay, so I'm not going to justify, but one can justify that, in fact, this is compatible with composition. Any way you break it down, it's not so hard to see. Question?
Sorry, before you erase it, could you maybe just like briefly summarize what all happened? I don't know exactly. For example, what is it that gives what operation in which vector space? What do you mean by star? Does your graph have a base point?
Okay, my graph does not have a base point. Can we do those questions one at a time?
Sure. So, for example, what exactly is it that gives an operation? Is it each picture, or is it?
Each picture like this, yes, each planar diagram like this gives you an operation. And by counting the number of strings around the outside, it tells you which space to take your inputs from and which space your outputs land in. Okay?
And then you give an example of the graph.
Yes.
And those were arbitrary loops in the graph starting anywhere,
Yep.
and ending at that same place.
Yes.
And then you just chose a factorization of the loops that you're going to multiply as P1, P2 star, P3, P4 star.
Right. So yeah, if you have even loops, you can split them in half. You have the there and you have the back again. This particular diagram only works for even loops, or this whole family of diagrams. Yep. And then you can contract them. You read the outside circle. You're welcome. Thank you. Okay. Now, subfactors also give some really interesting examples of planar algebras, but like I said, That's going to be on Thursday, not today. So I'm going to skip over that for now. And instead, I'm going to tell you about a different family of algebraic things we can draw diagrams for, which we've already seen in maybe all of the talks today. And so I would be remiss if I didn't also do this. Write down the definition of a monoidal category. Well, and that's an exaggeration, in fact. I'm going to say that a monoidal category has the following structures. A tensor and a unit object as well as associators and left and right uniter natural isomorphisms. Okay. The reason that I want to write this down is that there's a way to draw pictures of these things that we've seen, and well, I think there's some value early in this workshop on being really clear about the foundations here, about what it means when we draw these sort of pictures. Because if you've seen them before, you're like, yeah, okay. And if you haven't seen them before, you're like, maybe a little bit lost. So, okay. The pictures we're going to draw are pictures of the morphisms in such a category. And these are drawn in 2 dimensions. And so if you like, you can think of the objects as one-dimensional things. And then when we have a morphism, say f from A to B, we draw it as a box with a strand labeled A incoming and a strand labeled B outgoing. Okay, and so already our objects are not one-dimensional, they're 2-dimensional. They're strands, right? Well, okay, really, when we draw a strand like this and we label it A, we think of this as the identity on object A. Okay? Okay. Now, what does the tensor product mean in this context? So, if we have 2 objects, and we have A and we tensor it with B, we can think of this as drawing a strand for A next to a strand of B. Okay? So tensor product is horizontal composition. Okay, so we could equally well label this strand by have one strand labeled by A tensor B, but we can also draw this as just an A next to a B. And the reason we might prefer this is that then you can compose, if you have, say, F going from A to B and G going from C to D, you can denote composition just by putting them down. Sorry, you can denote tensor just by setting them down next to each other. Okay? And so this is the same thing as having this. And I haven't left myself much space, but I'm going to tell you what to do with the unit. And it doesn't matter that I haven't left myself much space because we don't draw the unit. Okay, the unit is the empty diagram. Okay, right? We have these uniter isomorphisms that tell you that one tensor A is just the same thing as A, So putting a 1 down next to an A is just the same thing as having an A by itself. So this is like an invisible strand, if you like, right? You could draw a strand with 1 on it, but it would be allowed to pass under and over and around everything else in the diagram. Okay, so this is the empty diagram. Okay, and so there is the fact that these drawings have mathematical meaning is a contentful statement. And I'm not going to prove it, right, but it's at least worth writing down. Okay, so I took this from the Hunin and Vickery book, but it's almost certainly not due to them, due to other people. But the statement is that a well-typed equation between morphisms in a monoidal category follows from the axioms of a monoidal category if and only if it holds true in the graphical language. Up to planar isotopy. Okay, so let me just give an example. Right? If you're working on the level of categories, if you're working algebraically and symbolically, and, well, I'm going to end up giving this example diagrammatically instead of categorically, F, G, H, and K. Okay, there's multiple directions of composition. So composition of morphisms is a vertical composition, D, E, F, whereas tensor is this horizontal composition. Okay, and so there's a theorem here that says that we could build this diagram up in 2 different ways, right? We could take H compose F and then tensor that with K compose H, K compose G. Or we could have done the tensor first. We could take H tensor K, and we could compose that with F tensor G. Okay, and the claim is that because this is obviously true in the graphical language, then it's also true in the monoidal category. Okay, and the proof of this, I think, is just kind of seeing that anything you can get from the axioms, you can get by combining these diagrams, these moves that you're allowed to make in a certain sequence. Okay, and there's one more thing that we need if we're going to connect back to planar algebras, and that is rigidity. Okay, so a rigid monoidal category has left and right duals for all objects, and it has the snake equations, right, that look like saying that this equals this, where we take this and we break it up right, so here's x, and then this is x star, and here's x again. Right, so we have a co-evaluation that goes from the unit object to x dual tensor x. And then at this level, we have evaluation combining x and x dual. And the thing about having this is that it really enables us to do planar isotopy freely, right? To wiggle things around and only worry about them topologically and not pay attention to directions like up and down.
I think in standard notation, this x dual should put star on the left.
Thank you. Okay. Okay, and so given a monoidal category, we can get a planar algebra from it by choosing one particular object and zooming in on that object. Okay, so pick x in C, a rigid monoidal category. And then only look at pictures you can draw where all of the strands are labeled by x. Okay? And if you do that, you very quickly get bored and stop labeling your strands at all. Right? And then your VK is the endomorphism space for tensor products of x. Okay? If you have a diagram and you have a strand with n things coming in and n things going out, then that means that you have n copies of x tensored together along the bottom and along the top, and what you put in there, it must be some map between those things. What's that?
K equals to n?
Yes, thank you. Yes. Okay, so this is a planar algebra. Okay. And, well, if these are really two sides of the same coin, why bother with both of them? Why not just decide that this one is more general and give up on this one? If you have two different points of view, there are going to be some things that look different in one point of view than the other one. And in particular, planar algebras have a different notion of smallness that turns out to be interesting. So if you have a monoidal category, you might look at the number of simple objects you have. If that's a finite number, then what you have is a fusion category. And the number of simple objects, the rank, gives you a measure of the complexity of the category. Okay? And in planar algebras, historically, we've taken a slightly different measure of how big it is, right? It only has, it's singly generated, but we have a different idea about how to measure the size. And the answer is to look at the Frobenius-Perron dimension of this object x. Okay, and now what is this?
So does this category have to be semi-simple, or at this point it's not important?
Oh, probably it does. I don't ever think about things that aren't semi-simple, so let me stick that in to be safe. Okay, so the Frobenius-Perron dimension is two ways to think about it. Okay, so if you take the Grothendieck ring of your category, and you can find a ring homomorphism to R such that for all simple objects x, this Frobenius-Perron dimension is positive. Okay, now you might think that's not a lot of information, but actually it uniquely characterizes it. Another way to think about it, a little more concretely, is that if we're in a fusion category, so you have a finite number of simples, then we can look at for fusion categories, yes. Yeah, and if you would like to see treatment of this that deals with the subtleties that I'm skipping over, EGNO has an excellent treatment of it. So if we, for our fusion category, if we take X tensor Y and we decompose it into simples, we get these coefficients, these C's, these numbers that show up. And so if we make a matrix of them, okay, where we let Y and Z range over the simple objects in our category, then this is a non-negative matrix, and its Frobenius-prone eigenvalue is the Frobenius-prone dimension of this object X. Okay, and so this is saying that we measure how big X is by looking at what happens when we multiply by it. When we multiply by it, do we get things that are very large? Do we get things that stay small? Do we get things in between? And so this is a way of saying how big X is. And this number can tell us a lot about this planar algebra. And this seems like a good point for me to stop. So.
Questions? Any questions? Yes, please. In this last example, where the added isomorphism of constant, is X required to be self-dual?
Yes. Yes, I'm assuming that.
And if it's not, then can you just open the direction X star?
Yeah, that's right. I am not requiring that today.
Because all of your examples seem to...
Oh, I thought I drew at least one. Temporally leave does. And a lot of these ones that are on the board now do. In the subfactor context, yes, they're always even. But in a more general context, you don't need them to be.